In its opening days, the anonymous Aux Alpha deployment processed 2.11 trillion prompt tokens. By contrast, it output just 25.4 billion completion tokens. That creates a staggering 83-to-1 input-to-output ratio. This is the defining fingerprint of agentic software engineering. This traffic volume is driven entirely by autonomous programming frameworks. Hermes Agent alone accounted for 731 billion tokens, while Claude Code followed with 434 billion. These systems operate by injecting massive state context, entire abstract syntax trees, logs, and source code, all to generate minimal, surgically precise code edits. Standard consumer chatbots operate in reverse. Short human prompts yield long explanatory outputs. For modern AI software development, generating code is the easy part. Sustaining autonomous workflows is entirely a problem of massive context ingestion. Managing this volume relies on a tri-protocol API gateway sitting directly between the clients and the Stealth core. The gateway simultaneously supports the standard OpenAI chat completions endpoint, as well as the modern OpenAI Responses API, designed for streaming agent loops. It also offers native Anthropic messages compatibility, accepting multimodal inputs like PDFs and images, while supporting built-in tool calling configurations. Because these three specifications operate on a single endpoint, teams can route traffic without rewriting a single line of their orchestrator adapters or client code. Currently, this preview is priced at $0 per million tokens, though the Stealth provider explicitly states that prompts and completions are retained. High-capacity reasoning engines are no longer confined to closed ecosystems. They are accessible as an interchangeable utility across open routing platforms. Transmitting a 1 million token context window repeatedly across a multi-turn agent loop creates an immense computational burden. Without mitigation, prefill latency destroys the system's interactive speed. This diagram illustrates prefix caching in action. Aux Alpha maintains an average cache hit rate of 82.13%. When a 100,000 token repository context is sent, 82% of it is frozen in memory. Only the 18% marginal delta requires fresh attention computation. In a standard 20-turn session, calculating the prefill from scratch would cost 2 million tokens of compute. With the 82% hit rate, the effective burden drops to under 450,000 tokens. To capitalize on this, developers must ensure that prompt headers and static system instructions remain perfectly identical across every API request. Prefix caching is the exact economic engine making long-horizon, autonomous coding loops possible in production. The output mechanics of the inference core are equally critical to its operation. Rather than generating flat text completions, Aux Alpha exposes its step-by-step logic inside a structured array called reasoning details. This introduces a strict operational rule. The client harness must capture the entire reasoning payload and inject it back into the model on every subsequent conversational turn. If an orchestrator strips out these details, the model's deductive context shatters. It is forced to recalculate its logic from scratch on the very next turn, immediately inflating response latency. It also triggers context fragmentation. The model forgets the subtle architectural constraints it identified steps earlier, frequently leading to contradictory implementation strategies halfway through a complex code refactor. Access to a frontier AI reasoning engine provides zero advantage if the client-side architecture fails to protect the model's deductive continuity. This graph plots the model's latency distribution. While median time to first token is relatively low at 4.23 seconds, the end-to-end request times show severe dispersion. At the extreme end, the P99 end-to-end latency reaches 278.6 seconds. That is a 14.3x increase over the median completion time. These massive delays are generated entirely by internal chain-of-thought expansion when the model is evaluating intricate repository architectures or dependency cycles. Once the internal thinking concludes, the system accelerates, pushing burst generation speeds up to 80 tokens per second for the actual code output. To handle this variance, client web requests require a minimum configured timeout of 300 seconds, and they must implement server-sent event streaming to keep the connection alive while the model thinks. Relying on standard web application networking defaults will cause an orchestrator to silently drop up to 5% of its most valuable reasoning work. The final limitation in sustained agent loops is the breakdown of structured tool calling. Telemetry shows an individual tool call error rate of 2.09%. In single-turn tasks, this appears highly reliable. This graph maps that specific failure probability across a 30-step software engineering trajectory. The reliability compounds negatively with every action. By step 30, the agent has only a 53% chance of completing the task without encountering a fatal JSON formatting or schema error. Even the most capable models cannot guarantee the completion of long horizon tasks natively. They require client-side interceptors to automatically catch and retry malformed JSON outputs. Community researchers currently assigned a 90% confidence interval to the hypothesis that Ox Alpha is a preview build of Jipu AI's unreleased GLM 5.3 series. Regardless of its true origin, this deployment proves that massive context reasoning engines are actively commoditizing into interchangeable backends. This shifts the engineering challenge entirely toward what we can call the locus of reliability. Success in autonomous programming relies on managing cache prefixes, perfectly preserving conversational reasoning states, and engineering resilient tool retry loops. As reasoning models transition into universally accessible web utilities, the ultimate value in AI software engineering belongs strictly to the builders of the client harnesses.